In this video, we will be looking at phase lag for subsurface pits in aluminum using the multi-frequency Zetec MIZ-27 impedance plane test instrument. Now for this demonstration, I'm using a tiny differential, self-comparison differential actually, surface probe. You're gonna like the signals from this probe because they look like what you would see when you're doing a bobbin probe exam, doing tubing. The dual polarity differential signals are real nice because they're easy to spot. Hopefully everybody can see those flaws. If not, might be time for a new eye cert. You know, you only need one good eye to perform data analysis. And I actually knew at least one analyst with only one eye. I have no idea how he did it, because when you're looking at, you know, difficult to analyze data from miles and miles of tubing, each 12-hour shift, you know, that can lead to eye fatigue and visual eye strain. It's hard enough to do with two good eyes. All right, so there is, just by self-comparison differential, scanning over the three different EDM notches, 10 mils deep, 20 mils deep, 50 mils deep. One more quick scan. And in this differential probe, not sure if you can see it or not, but there's a little line on this side of the probe. And you need to keep the orientation of your probe with that line facing the direction of travel so you can hit the flaw with the right angle of attack. All right. So everything's set up there. Now for my test frequencies, I'm using 4. 1 megahertz, green. The red 600 kilohertz, purple is 200 kilohertz, and blue is 50 kilohertz. So we're going to be looking at some various depth flat bottom holes, all subsurface, on these different frequencies to see what happens to the phase lag. So now the configuration of this sample, it's about 1/8 of an inch thick of aluminum. Then I took about a 3 millimeter diameter drill bit and I drill a shallow hole, a little bit deeper, all the way to the left end where I have a through wall hole. I made 3 rows of pits, very similar. And then I covered this block with aluminum foil. 1 sheet closest to me, 2 sheets in the middle, 3 sheets on the far side. And the shallowest flaws are on the right end. So basically, I'm going to start placing my probe in the material, hit null because null is your friend. We're going to try to find the first pit, and it shouldn't be difficult. Shouldn't be too difficult. What, did I speak too soon? All right, there's a nice pit right there. Where is it again? Where is it? I even know where they're at and they're hard to find. Do I have the orientation of my probe correct? That's important. Should be going right about, where in the heck is it? Make sure I'm not on the thick end. Coil orientation, there's my probe. There's a pit, okay. So let's take a look. The reason that I have nice amplitude on these signals is because they're not far below the surface at all. Only 1 sheet of aluminum. But look at the phase lag on these different frequencies. 1 megahertz being green has the most phase lag, and it's not a lot. But then again, this is very close to the surface. So you've got about 20 degrees phase lag on the highest frequency, and you got just about 0 degrees phase lag on the lowest frequency, 50 kilohertz in blue. Now let's go over one that's a little bit deeper. Now you can see the phase on 1 megahertz has increased. It has increased some. So your eddy current test instrument is basically using the test probe and its magnetic field to survey the material at all depths, providing you're using the right frequency, of course. And what your test system does is it returns the information to your output, and it lets you analyze the signals based on signal phase and amplitude. So because the higher frequencies take longer to send and receive the information, you're going to have more phase lag than you do with the lower frequencies, like 50 kilohertz, for example. All right, let's move on to the next flaw, if I can find it. Should be one right about here. Now, obviously, I'm not holding my probe right because I'm not getting a very good response. See how that's better? I'm holding my probe in the right orientation now. That's a real nice one. Once again, the signals are getting a little bit bigger because the volume of my hole is increasing at this end. Should be another one right there. Yeah. All right, and then there should be a through wall hole in here somewhere. Okay, that's the through wall hole underneath one sheet of aluminum. So using our normal phase analysis methodology, you can see that the amplitude of our signals got larger with the bigger hole, and the high frequencies had the most phase lag. One more time, I'm just going to locate the shallowest pit. Notice the low amplitude and the fairly low phase lag on every channel. And then I'll go to the through wall. Much larger signal amplitude and increased phase lag because there's more material missing. Eddy currents have to go deeper to get all that information and return it to your output display. All right, next we're going to move on to 2 layers of aluminum. So these are slightly more subsurface. All right, where are we at? Right about here, there's one, okay. So that's a shallow subsurface flaw. Maybe we need to get a little bit deeper to get some action here. Okay, that one's a little bit better. Notice the phase lag on 1 megahertz. It's quite a bit more. That's because now we're penetrating deeper into the material to see those flaws. And if you look down at the lowest frequency, 50 kilohertz, still not a lot of phase lag because lower frequencies penetrate deeper, quicker than the high frequencies. Okay, there's that one. Now we're going to go to a little bit deeper. Amplitude gets larger, phase lag increases, most noticeable on the higher frequencies. Then we got one here, and then this is going to be our through wall right about not there. That's the end. Where is it? Right there. So that's a through wall, but keep in mind, it's underneath a couple sheets of aluminum. Now we're going to go to the final layer, 3 sheets of aluminum foil. We're going to start off with the shallowest indication, right about there, maybe. Right about there. Right about there. So, which one of those frequencies sees that the best? I'm going to say not any of them real good. I mean, there's something there, but it's not very profound. We'll go a little bit deeper. A little bit deeper right in here. There's one. You can really see this would be a prime time to use alarm gates because I have to spend time focusing on my test material surface to make sure I'm holding my probe perpendicular or normal to the surface. But when I do that, I can get right over the top of that flaw for demonstration's sake. Now the biggest signal comes from 50 kilohertz. That's the data in the blue. Let's skip ahead and get a little bit deeper here and get some more action. All right, there we got one right there. You know, this small diameter coil is not very penetrating. The coil itself is probably only maybe 3 millimeters across, max. Now, the reason we get these kind of wider signals is because the width or the diameter of the drill bit is about the same width as the coil. If I wanted to get more profound indications, an increased probability of detection, I would use even a smaller self-comparison differential coil. But this is the only one I have. Otherwise, I guarantee it, I would make a video with that. You know that. Now, I was slightly in the wrong spot for my through wall. The through wall is right there. So notice how much smaller that is under 3 sheets of aluminum. I'm going to go back and try to find the through wall from the thin sheet, and it looks like it's about right there. Yeah, right there. See, that's a good size signal. Right there, right there, right there. Come on, get on it. So that's a pretty good size signal. Only 1 sheet of aluminum. But now when we go to the through wall for 3 sheets, look at how small it is. And increased phase lag. So coil diameter is very important for finding these small subsurface pits. Test frequency is important. And as the flaw gets deeper and farther subsurface, you can have more phase lag on every frequency. So I hope you enjoyed the video with all these colors on the MIZ-27. End of lesson.